Hello everyone, welcome back to the lectures. Let's firstly do a review what we have talked about in the last lecture. In the last lecture, we have talked about the cross-validation CV, and this is mainly used for tuning the hyperparameters. And I have covered two methods. The first method is the K-folder CV. So in the K-folder CV, we will divide our data or our training data into K folders. So here, if we divide the data into five folders, that means we will uniformly divide our training data into five parts. And for each hyperparameter, we will train five models here. So in the five models, we will get five arrows. And for each of the hyperparameter, we will take the average of these five arrows, and then we will change the hyperparameter, and then do this again. Thus, eventually we can get some diagram like this. As we change the hyperparameter, our average value would also change. And then we just pick the minimum arrow corresponds to the optimal eta. And therefore, this is the process when we use the K-folder CV to tune the hyperparameter. And another case is that the leave one out CV. The leave one out CV is a special case of the K-folder CV because in K-folder CV, we divide the data into K data sets. But here in leave one out CV, we make each folder just one sample. So here, when our folder equals to our sample number, so here each folder will be just one sample, and this folder will be one sample. This folder will be one sample, and so that's why LOOCV is a special case for K-folder CV. And as you can imagine, of course, LOOCV will require longer time to get the results because it has much more folders than the K-folder CV. You have n samples, and it will have n folders here. Okay, that's a brief review on what we have talked about in the last lecture. And so here in this lecture, I want to cover a slightly different topic also in linear regression problem, that is feature space mapping and linear regression. Okay, and mainly focused on the feature space on this concept. And you should keep in mind that this concept, feature space mapping, is not only exists in linear regression, it also exists in almost all the machine learning algorithms because all machine learning algorithms require the features. And so it will all connected to the feature space, this concept. Okay, as usual, I will start with an example or more examples. I have two or three examples here to help you understand this concept. Okay, suppose we have a very simple data set like this, and here we have just one variable or just one feature. We have just one feature, so we can visualize it in the plane. So X is the feature we have, and Y, so Y is the label, Y is the prediction. And suppose our data set is like this. We have a point here, we have a point here, we have a point here, we have a point here. So we have five data, we have five sample in our training data set. And let me give you the coordinate each one. So this is 1, so this is minus 1, 1, obviously. This is 0. So we can have the coordinate of each node, right? So this point, maybe this is x1, and its coordinate is minus 1, 0. And here you should clear that. So this one is, we know it's x coordinate, but here x is feature. So this number minus 1 is its feature. And here we know this 0 is its y coordinate, but here it's is its label. So, okay, I want to adjust this. And let me continue to write this. And this is maybe x2. And of course, this is the feature. And the second number is the prediction. And this is x3, 1, 0. And this is x4, 0, minus 1, obviously. And this is x5, of course, 0, 0. Okay. Suppose this is a very simple linear regression problem, and I want you to fit a model on this data set. How you can fit the model? I want you to use the linear regression, a straight line model, a linear model. Maybe you will see this is your model. Get this is the model. So is this model good enough? Or you see you can so maybe this is your model you get, or something like this. So we have two models here, but are these two models are doing something very good for us? Can they make a very good prediction? We doubt it. Of course we doubt it, because we can see all these two models cannot fit the data very well. And you may say that's because the data is very strange. Yeah, it's strange distributed, but that could be the case in our real scenario. So how can we do a better prediction by using this simple data set? We have some methods here. So this is called feature space mapping. And here, let me give you some definition here. So here, if we have only one feature, we call this feature space one-dimensional feature space. And we will use a notation like this. This one also used in vector space. So this one R1 means it's one feature space. So this is our one feature space problem because we only have one feature, that is X here. And of course, if we have two features, that would be R2 feature space. So here in previous house prediction example, and this is not the house prediction example. In our previous example, if we use the area of the house and the number of rooms as the features, so here if you use two features, that would be a problem in the two-dimensional feature space. So in this problem, the feature space belongs to R2. That is very obvious because we have two features here. Okay, this is easy to understand. And let's get back to this example here. And I said we have some methods to make better prediction. And the methods is something like this. We will define a function that is phi and x. So here, the name of this function is basis function. We will use this basis function to map this one-dimensional feature space to higher dimensional feature space. Because once we put something in higher dimensional space, you will see some magic will happen, and we can make better predictions here. Okay, and let's suppose I gave you this basis function in this example. Maybe the basis function is something like this: x squared and x raised to the power of 4. So here we just have one feature, and so this is our one feature space. And once we put all these one features, and you can see we use this basis function. So for each point, we can have two features here, because we have x to the square and x to the raised to the power of 4. So this is one feature, and then this is one feature. So we increased our feature from one feature, from this x coordinate, to two features. Okay, so here this phi x will belong to R2, and this basis function is usually nonlinear. Okay, you can see this is nonlinear mapping here. Okay, let's do the calculation then. Let's firstly calculate what the basis function will do on x1. That is our first data. So the feature of R1 is just -1, because here 0 is the prediction, is the label. So here is -1. We put this coordinate -1 into the basis function. It will give us two features, 1, 1, obviously. Similarly, we do it for x2 equals. So x2 feature is 0. So here two features are 0, 0. Very easy. And phi x3. So phi x3 also 1 here. We got 1, 1. Also similarly x4. It's 0, 0. Phi x5. 0, 0, of course, because it's the origin. Okay, so here you can see that by using this basis function, we changed our feature space from one dimension to two dimensions, right? Because here, these two numbers are all our features here, our new features. So here they all belong to R2. And if our feature space is R2, how can we visualize our data? If we have two features, yeah, it will go to a higher dimension. We can still visualize it. So it will be in the 3D. It will be three-dimensional if we want to visualize it. Let's try to visualize it. So here, this axis is still our prediction, y. But here we will have one more axis here. So let's suppose this is the x to the x square. So this is the first feature. And we have another axis. Let's see, it's x raised to the power of 4. So this would be this feature, the second feature. And let's draw our training sample. Maybe I will make the line longer. Okay. And let's also use the green dots here. Let's find those 5 points easily. Let's find the Okay, let's find them one by one. So for the first one, this is 1, 1. And remember, their label is not changed. Their label is still, this one is 0. So the first one would be 1, 1, 0. Let me firstly, so this is 1, this is 1, and this is 1, this is -1. First point is 1, 1, 0, and would be around here. So this is 5, x1, okay? It's in this horizontal plane. And the second point, 0, 0, and what's its prediction? 0, 0, 1 here. So it's 0, 0, 1 would be here, right? So this is the 5x2. Okay. About 5x3 is 1, 1, 1, 1, 0. Also, this point. And these 2 points are overlapped. How about 5x4? 5x4 is 0, 0, minus 1. So it's here, 0, 0, minus 1. And this is 5x4 here. Okay, last point. It's 0, 0, 0. It's the origin here. Okay. So this is a 5x5. Okay. So now you can see if we map our feature space from a low feature space to a higher feature space, we can see that now the position of our training samples are changed to these points here, to these positions. And what the mapping is doing for us is that this mapping is like folding this x1 to these positive parts of x-axis. It's doing something like this. And the benefit of doing this is that we can see that if we want to use a linear model to fit these points, we can find a very good fit, right? Because these 3 points are in a line, and these points is out of this y-axis. So we will find a very good plane to fit these data, something like this. Maybe we find a very good model. Like this. Let me draw a straight line here. Okay, you can see you will be very confident that you can find a plane, a linear model like this to fit these 5 data in this R2 feature space, because they actually lie in a plane. So you can find a plane by doing linear regression problem. You just need you just mapped your feature space from 1 dimension to 2 dimensions, and then you can find a better model. So why would we still do the linear regression like this in the R1 feature space? We can do it in R2 feature space. So that's why we want to sometimes put our data into higher feature space here. Okay, and this is the first example, I think. Let's talk about second example. Example 2. Okay, this is the second example is also similar to this one. I just use this picture here. Also, similarly, if you can see that this is so this axis is our prediction, y, this axis, and the horizontal axis is our features. It's similar to this problem, but we have more data, and the data is distributed in a circle, maybe in a circle like this. So if you want to do the linear regression in this feature space, maybe you can find a line like this, find a straight line like this, but you will not be very sure that if this is a very good model for you or not. So I think most people will say this is not a good model, because when you calculate the errors, when you calculate the distance of each sample, you will have a very large error here. You don't want this kind of large error, so you can apply the 5x here to map your feature space from one dimension to two dimensions here. So this one, it also maps to two dimensions because it has two axes, and this one is also its prediction here. And so if you do this, if you map it to higher dimensional space, you can see that the data are differently distributed. They may be distributed like this one. So you can confidently find a line to fit your data, and you will see, oh, this one, when you calculate the arrows of each node, the arrow will be obviously smaller than this arrow, right? So this model is better. Okay, that's another benefit. And another example is actually what we have talked about, but I didn't point that out. Example 3 is what I have called it polynomial regression. We may be familiar with polynomial regression. We just use polynomial to fit the data, but it is actually doing the feature mapping for us. For example, in the example we have used, suppose we use 4 degree, m equals 4-degree polynomial to predict something. Y hat is our prediction, and our formula we said is something like this. This is bias, and x1, omega 1 x, and this is our feature. We just have one feature, and then we have omega 2 x raised to the power of 2, omega 3 x raised to the power of 3, x4 raised to the power of 4. We will stop here because we define it to be a 4-degree polynomial. So here x is our original feature. What is this? X power raised to the power of 3. You can see them as a feature mapping. If you see this x raised to the power of 2 as a whole part, so this is nothing but another feature here, and this one is nothing but another feature. This one is another feature. So here, by using this polynomial, you have actually mapped from one dimensional feature space to 4-dimensional feature space here. So here it will give you some polynomial regression, polynomial fitting like this. And here we can write what is the basis function for polynomial regression. This is also very simple. Basis function for polynomial regression is something like this, yx. So the first one would be still x, right? Because this is also x. And another one would be x raised to the power of 2, x squared. This is this one. And this is raised to the power of 3. And I will take a transpose to make it a vertical, a column vector here. And here, so we can see that this phi x actually maps our feature space from one dimension to 4 dimensions here. You need to see this one as a part. See this one as a part. When you see this one as a whole part, it's nothing but another feature, another new feature based on this x. And this feature is actually you created it based on x, and that makes sense. So this is the third example I want to give to you. I think after I made these 3 examples, you will be very clear what we are doing in feature space mapping by using the basis function. We just make our feature space to higher dimensional feature space. Okay. After the examples, I will give you some formal definition here. Okay, phi x is actually very important in our feature space mapping. And this one, what the basis function is doing is that phi x basis function maps feature space. We will use some notations here from RD. So you remember we define this capital letter D as the number of features we have. If we have 2 features, the D is just 2. It's easy. 2 RM. And here we have a new letter here. So M denotes the new feature space. If we map this one from 1 dimension to 4 dimension, and also here D equals 1 and M equals 4. And this is also easy. And I should point out that M would be greater than D because we will increase the feature space, not decrease. So M would be greater than D. And then we will have the new model, new linear regression model in RM, in our new feature space. So higher feature space. And I write the model for you. It's the same. Y hat equals omega transpose phi x. And here we will use phi x here as our new feature space. Before this, we just use x, right, for each prediction. But now we have this mapping, and so we use this new notation phi x to denote this x before. And so well, this omega. So this omega would be our new weights in the new feature space. So it's something like this. This is our weights in the higher dimensional space. And so omega will belong to m plus 1. So this plus 1 means we will still put the bias term into the weights vector, because here we don't have the bias term plus something, so we include this bias term by this plus 1 here. And so our objective function is still the same. We use the residual sum of squares. So the equation is something like this. We still have n samples. The number of samples is not changed. It's still capital N. And our new prediction of each node, of each sample, is this one. So this is the prediction of each data. And then each data, we minus its ground truth. So remember, this is the ground truth. And we take a square. So this is our objective function. We need to minimize it. And you also need to go through the similar calculation I have done before. And let's write for you similarly. We need to, this is the arrow function, so we need to minimize the arrow. We need to minimize the arrow function to obtain omega star. So omega star is the optimal weights, is the best weight we want to get. So this one, omega star equals argmin. You remember what is this notation? So here omega belongs to R n plus 1, I think, and RSS omega. So this is this function. And I will not go through the calculation. It's the same calculation as before. The difference is only that we are doing this in a higher dimensional feature space. Before this, we are doing in this RD, but now we are doing in RM feature space, and the calculations is all the same. If you go through the calculation, you will get something like this. So the optimal weights is still phi transpose phi. You take the inverse phi transpose y. Okay, so this equation is similar to the linear regression closed form solution we get. Before we get a solution like this, x transpose x inverse x transpose y. Before we get a closed form solution like this, and you can compare the x and phi. They are actually very similar. This one is the features feature information in RD. But here this phi, letter phi, is a matrix that contains the feature information in higher dimensional feature space, that is Rm. This is the only difference. So here I will point this out, where phi would be like this, would be phi x1 transpose and phi x2 transpose, or goes away to phi x capital N transpose. Because we have n samples, we will have here. Okay, so what is this one? This one, if we don't see this transpose, it's a column vector. We take a transpose, it will goes to a row vector. What is phi x1? Phi x1 is the features you get on the first sample after doing the mapping. It's actually this one. This is your phi x1. This is your phi x2. This is the feature you get from the first sample after doing the feature mapping. And this is also the same. Here, this phi x1 is the new feature space of your first sample. And this phi x2 is your new features of your second sample. And this is all the same. And so this one, this is a matrix. This is a very big matrix. And this phi is very similar to this x. We say that this x is also a matrix. This phi is a even larger matrix. And so here it belongs to a dimension like n. So n is the number of rows. We still have n samples, so this is still n. And we have n plus 1. This n plus 1 is the number of columns. So let me find. So here, yeah. So here, because we have included the BIOS term, so in this phi x1, the first letter would still be 1, and then you have your other feature space. So that's why we keep this as m plus 1. M is the actual feature you have, but this plus 1 means you include the BIOS term, because here is m plus 1 feature space. Of course, here you will have m plus 1 rows to make this vector to be so they can be multiplied together. Okay, and this makes sense. Okay, I think that's all I want to cover in this video. I firstly gave you 3 examples to show why we want to do the feature space mapping, because sometimes we cannot get a very good model in the lower feature space. So we want higher dimensional feature space. You will find that if you do the regression problem in higher dimensional feature space, you may find some very good model. And here I give you the new closed form solution for the linear regression problem by these 5 metrics here. And this 5 metrics is very similar to this X matrix before, but we just do it in a higher dimensional feature space. Okay, I think that's all I want to cover. Thank you for watching.